Hey guys, so welcome to the last video of covalent bonding. I do realize that we have not talked about part 1, but I wanted to make sure you watched part 2 and got that familiarity before the test. This is all covering intermolecular forces. So in the last video we covered polarity. In this one we're going to cover the forces that really hold together a bond besides just the fact that it's a bond. But there are other attractive forces that you need to be made aware of. In regards to information for your test, because I know that's pretty well all you guys are worried about, I will in class specify what I feel is more important to know and what's not. I'm not going to get into super details on like the dipole interactions and what creates a dipole and anything like that. I feel like that was a little bit confusing in the last video, and we still haven't talked about that in full detail. Really, I just want you to know that shape and electronegativity are going to help determine what kinds of interactions and what the molecule, what kinds of properties the molecule has, just based off of the different lone pairs, the different bonds. So this all resorts back to the VSEPR theory and that shape. So again, if you have any questions at the end of this video and you don't feel comfortable asking me in class, please make sure you're asking me on the videos or an email or just some way of telling me that you don't understand something. So the 2 points that we are going to focus on in this video, or we're going to be able to distinguish between the 3 types of intermolecular forces. Really, there's 4, but 2 of the intermolecular forces are one type. So, and you'll see in this video what I mean, and then you'll be able to describe how chemical bonding and intermolecular forces influence the properties of compounds. So we'll kind of start comparing and contrasting ionic and covalent bonding. We will do a lab looking at both ionic and covalent bonds and to distinguish those 2 based on how they do in the lab. All right, so intermolecular forces. So far you've learned about intramolecular forces, and even though I haven't mentioned that term, we've learned about covalent and ionic bonds, and those are types of intramolecular forces. So forces that act within a molecule or a crystal. And again, we have talked about covalent and ionic bonds. Now, molecules also attract other molecules, and this attraction between molecules is known as intermolecular forces. So forces that are actually occurring within the molecule. So intermolecular forces are pretty weak in comparison to an ionic or a covalent bond. So in comparison to the actual bonds and the electrostatic between them, these forces are much more weaker, but they still give that attraction that's there. And a big thing you need to know is that based off of what type of intermolecular force you're dealing with, you'll see different physical properties of molecular compounds. So melting points and boiling points can change just based off of these intermolecular forces that are found. Water has crazy properties that you wouldn't expect just based off the fact of its hydrogen bonding. And I'm going to talk about that here in a second. So there are 4 types we're going to talk about: van der Waal forces, dipole-dipole forces, London dispersion forces, and hydrogen bonding. The true 3 that I mentioned in the objectives are these 3 here, the bottom 3. The van der Waal forces really is just a grouping of 2 of these. And in the next slide, you'll see what I mean here in a second. On this slide, the van der Waal forces is just a nice name for both dipole-dipole and London. All right, so the first type of force I'm going to talk about is the van der Waal force. And really, this is just a big grouping name for 2 different forces. So van der Waal forces are the weakest intermolecular force and consist of dipole-dipole forces and dispersion forces. So van der Waal forces are just like a grouping, and that grouping contains dipole-dipole forces and dispersion. So if you really want to look at the list on the previous slide, dispersion. All right, so dipole-dipole dispersion. So quick reminder, if you don't remember, we learned in the last video that a dipole is a molecule with 2 poles. And so basically what's going on is that the polar molecules, the positive and negatives, are orienting themselves so that they are towards the negative molecules are towards the positive side, and the positive molecules are towards the negative side. Sorry, my dog was making a weird noise, so I started looking at her, and anyway, that's not the point. And so that's a quick brief reminder of dipole. So how does that work with dipole-dipole forces? So dipole-dipole force is attractive forces that occur between polar molecules, and you should know that already. In order to have a dipole, you have to be polar. hydrogen bonded to fluorine is a great polar covalent bond. Because remember, fluorine is so electronegative that it'll take that electron away from hydrogen. It has that great pool that basically leaves hydrogen exposed and have nothing but a positive charge to it. So that positive charge will try to orient itself to the negative plate, if you will. So a molecule of hydrogen, so let's think of a different type of molecule. We'll think of hydrogen chloride. So H and Cl. This is a partially positive hydrogen atom and a partially negative chlorine atom. A collection of many of these molecules align themselves so that the oppositely charged regions of neighboring molecules are near each other, which makes sense, right? Like positive charges don't want to touch other positive charges. They repel each other. So basically all a dipole-dipole force is the attraction between positive end of one dipole and the negative end of a neighboring dipole. So dipole-dipole forces are very much similar to ionic bonds because they involve only partially charged, but they are still very much weak bonds. Not bonds, much weak forces. So these forces can be broken pretty well easily. In comparison, we have what's known as London dispersion forces. And what these are intermolecular forces that occur between all atoms and molecules due to the random motion of electrons. So basically what I'm saying is that everything has London dispersion forces. Everything. All atoms, all elements, all electrons, everything. London dispersion forces everywhere. So if I were to ask you a question like, which of the following forces is found in these molecules, you should always and forever know London dispersion forces are always present. And the reason why all atoms and all molecules experience London dispersion forces is due to the fact that electrons are always continuously moving. We've talked about this a few chapters ago, where in that electron cloud, you cannot predict the speed and the location of the electrons because they're either going too fast that you can't locate them, and if you stop them to find that particular location, then they're not moving. So not an accurate depiction of location. And so this is what was observed by a guy named Fritz London, and that's why they're called London dispersion forces, is that he looked at and he said that because the electrons are always continuously moving, all elements and atoms and molecules have a specific force, and this specific force can cause what's known as an instantaneous dipole or an attraction between different molecules just based off the fact that there's repulsion and interaction between electrons. Generally, in regards to London dispersion forces, the strongest molecule would be iodine, or I2, so a diatomic iodine atom. And these are generally stronger because of the fact that they have more electrons than those of the halogens. So fluorine, less electrons, so that that dispersion force is going to be weaker, and so it's going to have a much smaller melting point in comparison to iodine, which has a much higher melting point. So what I'm basically trying to say is that London dispersion forces, depending on what atom we're dealing with, will influence the melting and boiling points of those atoms just based off the fact of the number of electrons, because you have more ability for interactions within those two. So dispersion forces for things like bromine, chlorine, and fluorine are a lot more weaker than those for iodine. And I'm going to show you a table of this in class, so don't worry if you're like thinking this doesn't make any sense. I feel like that happens quite a bit. All right, and then the final type of force that I want to talk about is what's known as hydrogen bonding, and this doesn't seem like anything crazy, but it is an attractive force. You see, obviously, one of the most common molecules that I think of when I think of hydrogen is water, H2O. And maybe you're probably thinking the same things. And so I'm going to use water a lot in talking about hydrogen bonding. So hydrogen bonding is an intermolecular attractive force in which a hydrogen atom that is covalently bonded to a small, highly electronegative atom is attracted to a lone pair of electrons on an atom in a neighboring molecule. So what does that mean? So basically, water molecules have an attraction to one another, and this is what gives us that property. This is why water is not just seen as like a gas in nature. It has that liquid property because there's attraction between them. Obviously, it's not super strong because we see it in a liquid form, but it still has those forces. And so what's going on is that water contains hydrogen atoms that are bound to a highly electronegative oxygen atom. So remember, I'm going to give you a table, or I should have already given you a table in class of electronegativities. If you look at oxygen, oxygen is a lot more electronegative than hydrogen. So what it's doing is pulling that electron from hydrogens, making that oxygen extremely electronegative. So what we have here is a polar bond. So water is polar. So the partially positive hydrogen atom of one molecule is then attracted to the oxygen atom of a nearby water molecule. So this allows for a bonding of various water molecules. So you don't just see one water molecule. You're not just drinking one water molecule when you drink your water. You're drinking thousands and millions of them just because of these hydrogen bonds. And a lot of this has to do with the fact that there's a lone pair found on the central atom. That lone pair also causes that attraction. In class, I talked about the dipole-dipole interaction for water and how that overall dipole allows for that upward force. Those lone pairs cause that water molecule to be bent. And you should know this from the Vesper theory. And so what those lone pairs cause that it causes that attraction, which then allows for more attraction and more attraction and more attraction. So hydrogen bonding is typically more stronger. It's one of the stronger intermolecular forces. Obviously, it's not incredibly strong that you could easily not influence water to do different things, but still pretty strong forces in comparison to all of the other intermolecular forces that we talked about. This only occurs when hydrogen is covalently bonded to fluorine, oxygen, or nitrogen. Meaning anything else that's bonded to hydrogen is not experiencing a hydrogen bond intermolecular force. This is due to the fact that these three atoms, fluorine, oxygen, and nitrogen, all are super electronegative, and so they withdraw the majority of the electron from that hydrogen, and this leaves the hydrogen super deficient of that electron, basically exposing the positive charge within the nucleus. And that positive charge within the nucleus then allows for more attraction to other molecules of water or whatever molecules nearby. All right, in class, I am going to show you a chart comparing and contrasting molecular and ionic compounds, and I will show you I'll show you examples of intermolecular forces and the substances that are made, or the molecules that are. What I'm going to do is I'm going to give you examples of molecules, and then we're going to go over what types of intermolecular forces we experience. I will also give you a table basically breaking down the criteria for each type of force. If you have any questions, please ask me on Edpuzzle.